Okay, welcome to video 11.1. We're starting our unit on rotational dynamics. And we're going to start rotational dynamics the same way we started linear dynamics, talking about kinematics and motion. But instead of having things moving in straight lines, now we're having things spinning in circles. So let's imagine that we have a wheel. And this wheel is spinning. And let's mark a point on the wheel. So we'll say this point on the wheel. And we'll call that position theta equals 0. So when the wheel initially starts, that dot on the rim is lined up with that line there. And that's theta equals 0, but as it rotates, this dot moves. And so let's say at some later time the dot is over here. Now in this case the angular position would be the angle it's rotated through, which is theta. And theta we're generally going to measure in radians because the distance traveled, so theta is the angle, really, the distance traveled is the arc length s. And if we measure in radians, s equals theta times r, where r is the radius of the wheel. And that's why radians are useful. Also, some other things to remember, we sometimes measured an angular position in revolutions, and that's 1 revolution is 2 pi radians, and if you measure it in degrees, 2 pi radians is 360 degrees. You should be able to do the unit conversion. Now the next thing we need to define is angular speed, which will be given by the Greek letter lowercase omega. And it's defined to be the derivative of the angular position. And it's essentially the number, or it's the change in the angle per unit time. It has units of radians per second or rotations per minute RPM. And you'll need to be able to convert between radians per second and RPM. Now here's a nice little trick. If you take the derivative of theta, if you measure theta in radians, theta equals the arc length over the radius. But the radius is a constant, so it can come out of the derivative. And there we have the derivative of position versus time. ds dt is just the linear speed v. So linear speed or tangential speed, that's what we normally mean if we use the word speed or velocity without a modifier. And omega equals v over r, or v equals omega times r. That's a useful thing to know. And then we can also go on to define angular acceleration. Use the Greek letter alpha, is defined as the derivative of the angular speed, and through a similar process we can show that alpha equals the tangential acceleration divided by r, and in words we say that alpha is the change in angular speed per unit time. Now this notion of tangential acceleration, we need to separate that from the idea of centripetal acceleration. So if you've got some particle moving in a circle of radius r, we already know from last year in Physics B that anytime you have something going in a circle, it has a centripetal acceleration that's equal to v squared over r that points toward the center of the circle. But we always assumed that it was moving at constant speed. In this class, though, we have to consider cases where it's actually speeding up while going in a circle. And so in that case, you have centripetal acceleration that points toward the center, and you also have tangential acceleration that is tangent to the circle. And so you have, in this case, you would have an acceleration that points like that. Now, the angular kinematic quantities, theta, omega, alpha, are pretty straightforward. They're not difficult to understand. But what is a little bit tricky is the fact that they are all vectors, except technically for theta. Angular velocity and angular acceleration are vectors, and we need to be able to determine their directions. So let's say that you have a wheel rotating like this. What you do is you take your right hand and you curl your fingers in the direction of the rotation. So I'm going to try to sketch someone's right hand. So here's the right hand, fingers curl that way. Okay, it looks kind of like Captain Hook. And then the thumb points up. That circle is the thumb. God, that's an awful hand. Anyway, the net result is that the angular velocity vector, in this case, is out of the board. And if you remember, we represent vectors pointing out of the board as a circle with a dot in them. Now the angular acceleration can also be defined as a vector. So let's say that this wheel is rotating counterclockwise, but it's slowing down. Now because it's slowing down, the angular acceleration is going to be opposite the velocity. And so if we take our right hand and we curl it in the direction of the acceleration, the thumb points into the board. And remember, we represent that, a vector into the board, as a circle with an x in it. So you do need to know that omega and alpha are vectors, and you need to know how to find their directions using this version of the right-hand rule. And now here's where, if you understand regular kinematics really well, it will help you. The angular quantities are all analogous to linear quantities. Meaning, analogous means like. Theta is like x. Omega is like v, and alpha is like a. All of the, or rather, like tangential acceleration. All of the equations we know that relate x, v, and a, meaning the kinematics, will apply to the angular quantities. So the first kinematic becomes omega equals omega naught plus alpha t, where omega naught is the initial angular speed. The second kinematic becomes delta theta, the angle it rotates through, and that's equal to omega naught t plus 1/2 alpha t squared. And the third kinematic, omega squared minus omega naught squared, equals 2 alpha delta theta. Now one thing to note here is that delta theta can be greater than 2 pi. So for instance, if you say something rotates through 2 revolutions, delta theta would be 4 pi radians. So it does not reset to 0 when it rotates around. But now there's some other things. Let's say we have a graph of omega versus t. Well, if we have a graph of v versus t, a is the slope of that. So alpha is the slope of the omega versus t graph. Omega is the slope of a theta versus t graph. And also, delta theta is the area under an omega versus t graph. And all of this happens because omega equals d theta dt and alpha equals d omega dt. Everything I've written down here in this bottom part derives from these two expressions. That's why we love calculus. Now, speeding through our definitions, we also have the idea of period and frequency. The period of rotation, usually given by a capital T, is the time to make one rotation. So that's going to be 2 pi over omega is one way of expressing it. Or 2 pi r over v. There's a number of other ways. Typically, the period of rotation is only a useful quantity if the angular speed is constant. And then the frequency is the number of rotations per unit time, and that's just 1 over t, or the angular speed divided by 2 pi. We won't use that very much here, but you'll find it comes in very useful when we get to simple harmonic motion in our next unit. And so now we finally have an example. Let's say we've got a flywheel. Okay, go away. Oh, okay. You've got a flywheel that turns through 40 revolutions as it slows from a speed of 1.5 radians per second to a stop. Assuming constant angular acceleration, find the time for it to come to rest, and find the angular acceleration. Well, because it has constant angular acceleration, we can use the kinematics for the angular variables. And it's easier to find the angular acceleration first. So first off, we know the displacement. 40 revolutions is 80 pi radians, which is about 251 radians. We know that the initial angular speed is 1.5 radians per second. The final angular speed is 0. And we're looking for a and then t, or rather alpha. So we'll use the third kinematic to get the angular acceleration. Omega squared minus omega naught squared equals 2 alpha delta theta, which simplifies to alpha equals negative omega naught squared over 2 delta theta, negative 1.5 radians per second squared, divided by 2 times 251 radians, and we find that alpha equals negative 0.0045 radians per second squared. It's negative because it's slowing down and we made the speed positive. Now we want to find the time, and for this we'll just say, well, the time it takes is the change in the angular speed divided by the acceleration. So that's negative 1.5 radians per second divided by 0.0045 radians per second squared, also negative. And that works out to 335 seconds, which is about 6.5 minutes. So that is how we use the kinematic equations for the angular variables. And what I'm going to be checking tomorrow in class is questions 1 and 2 from chapter 11.